Okay, and meanwhile, I'll introduce the next speaker. Ron Bowen is Director of Public Works for Anne Arundel County, Maryland. Anne Arundel County is responsible for regulatory compliance with a Phase 1 MS4 stormwater NPDES permit, as well as defined pollutant load allocations for sediment, nitrogen, and phosphorus associated with the Chesapeake Bay TMDL. That's a lot of responsibility. Stream and wetland rehabilitation is a major component of the county's Phase 2 watershed implementation plan for the Chesapeake Bay TMDL, and we'll hear a little bit about how they're striving to achieve it.
Thank you. As I page through the slides here today, what I'll be providing you is a visual story of the existing conditions that we have on the landscape today within our headwater stream systems. As was noted earlier, Anne Arundel County sits on the Chesapeake Bay with 520 miles of shoreline, and the picture you see here is a condition of our one of our watersheds after a rain event. And the net result of why we see the kind of material that we see in that waterway is the erosion that's occurring within these headwater stream systems. And the colloidal clay material, the real fine material that's associated with the soils that are eroding, is what turns the entire body of water to the brown color, which obviously is eliminating any opportunity for sunlight to penetrate through the water column. And all of this is the dramatic impacts of changed hydrology as a result of urbanization that's occurred over time. One of the driving factors behind why we have focused intently on these headwater stream systems is with the promulgation of the Chesapeake Bay TMDL, and as we assess the conditions within our watersheds, we recognize and realize that the vast majority of the source of the problems, especially as it relates to sediment, was directly related to our stream systems. So also associated with that are the nitrogen and phosphorus. So the Chesapeake Bay TMDL is the driving force behind an obligation we had to meet relative to dealing with these conditions. One of the things that we've done within Anne Arundel County over the past 8 to 10 years, when the MS4 stormwater NPDES permits were promulgated, it obligated the local jurisdictions to do condition assessments of the watersheds and to develop watershed implementation plans relative to how to deal with those. And what we have been doing over those years, for each watershed, as we march our way through it, we have a consultant walk every mile of perennial stream and every mile of ephemeral channel, condition assessing and gathering a huge wealth of information relative to those existing conditions. We're probably about 2/3 of the way through the county in terms of completing that work, but what we have learned to this point in time from a physical habitat perspective, after us condition assessing roughly 410 miles of these stream systems, 218 miles, over half of those are severely degrading, convinced us very quickly that soil that's being eroded out of headwater stream systems is the vast majority of what's coming down into these tidal waters. Also, what we learned were that the sediment yields coming out of these perennial streams, as is listed here, once again, of that 410 miles that were assessed, roughly 344 miles of that has very high to moderate sediment yield. Once again, all as a result of the changed hydrology. When we look at the moderate category of this erosion that's taken place, what you need to understand is almost all storm events, after we erode to certain points, stay contained within those eroded storm channels. And the force of that water is exponentially increasing the rate of erosion in terms of eroding these streams deeper and wider. So we have to be very concerned about a very substantial amount of miles of that problem that's occurring. We also have been going through a multi-year process here of biologically assessing the condition of our stream systems, and the results of those study efforts at this point in time represent 72% of those stream systems are poor to very poor. For those of you who are not familiar with Anne Arundel County, roughly the top half of Anne Arundel County is where all our intense urbanization is occurring, and the southern half of the county is primarily agricultural, rural land area. If you were able to turn on only the poor, very poor dots on this slide and look at it from an overall perspective, what we find is these very poor to poor conditions exist equally across the entire county. So no matter whether you're in the historic urban areas or whether you're in the rural areas, the same problems with the biological conditions of our stream systems is occurring. That's largely because of the land use changes that have taken place. Urban development's different than the deforestation and the various farming operations and things like that. The important point is they're both having the same net impact as it relates to the stream systems and their biological systems. This, the dynamics of this erosion that occurs in headwater streams, as I mentioned earlier, in sizes, the perennial channels erodes them deeper and wider, as well as the ephemeral channels. As I also noted, as we progress through time with the amount of runoff increase in impervious area and the amount of runoff increasing, it's also accelerating the sediment yield. Another important thing to understand is that the soil that's eroding out of these stream systems has phosphorus associated with it, which has been sequestered in those forested floodplain areas over many, many years. And as this soil erodes out of the stream banks, some portion of that phosphorus comes back into solution and finds its way down into the tidal water, so it becomes another huge source. You'll see as I go through the slides that follow here that we've lost a lot of groundwater hydrology, as well as a lot of the floodplains and wetland areas have been robbed of the saturation of the soils. This is a slide of a storm drain outfall. If you're not familiar with storm drain outfall, we have pipe systems that we put in our roadways and whatnot. We collect the storm water and we try to very efficiently convey it down to the stream's edge, and typically that ends up at an outfall structure. This was actually a piece of pipe that's sticking out here. You can see obviously there's a huge, vast eroded area here. This pipe at one time was extended out to about this area where these rocks are in this eroded area. But in essence what has happened is the change in hydrology and the increased runoff has occurred over time. And as we discharged it out of this pipe, it exceeded the carrying capacity of that ephemeral channel and started an erosion process. And this is a classic example of this exponential rate of erosion we're occurring. It's an absolute huge void of sand and sediment that is eroded downstream over time. This particular outfall was constructed as part of a residential development back in the 1990s. You can see the example of the significant amount of sediment transport occurring out of it. This is an example of an ephemeral channel that has been restored. It was an eroding channel of the nature of what I had previously described. And the process that we follow here, and the way we reconstruct these voids, is we actually refill the void itself with a sand bed, and we construct these rock weir structures within the channel that we're trying to contain. These structures are designed to convey the 100-year storm event, keep it contained within the outside edges of the rocks themselves. And primarily what will happen is when you have a rain event and it enters the upward end of the system, it will actually flow through that sand lens as shallow groundwater. It's only in the very significant storm events where perhaps we have an inch or 2 inches of rain within an hour or two will this create sufficient runoff to actually see a surface flows through the system. So the important thing to understand is these restoration techniques actually convert a concentrated stormwater flow to shallow groundwater before it's introduced into the stream system. This next slide is a picture of that same structure after it's had a number of years, about 5 years, to allow the vegetation to establish itself. You can see the rock weir structure here, the moss and stuff that's growing on it, but the important point to visualize here is it's become part of the understory, and you never recognize that you're conveying these stormwater runoff volumes through that system. The next slide here is an intermittent stream channel where we get intermittent flow in a channel. It's not perennial, it doesn't flow year-round, and it's not ephemeral. It has gets some base flow in it. But what you'll recognize here is that how they're disconnected from their floodplains. So this intermittent stream, was once connected up at these levels as the water came down through this forested area. It's disconnected the stream itself from the floodplain. With the stream up here, these soils will be saturated. You can see that it's dramatically reduced the saturation of soil. we've lost the groundwater hydrology, so there's a much less amount of base flow that finds its way into the stream. And we have the issue of the amount of phosphorus that is come out of the soils as the rain events pass through the system. This is a picture of the prior one where we've refilled, once again with sand. We've created the shallow groundwater conveyance system. We've created these step pools that work their way up through the landscape. They serve as an area of storage, but they also serve as a means and methods of decreasing the velocity of the flow through the system. Once again, those rock weir structures are incorporated in here to contain the storm events to prevent these things from re-eroding in the future. We reconnect to the floodplain, so you see a lot of water here that's on the surface that reconnects into these forested floodplain areas. We've eliminated the sediment erosion itself. We're also getting some degree of water quality enhancement as this water flows through the system. This particular flow rate that we see through the system is after a relatively significant storm event that had occurred. And you can see how it filled the stream system to the vibrant flow that it currently has. If we have another month or 2 months, or if we get into periods of time like that where we have drought conditions, what will happen, and this is a fairly steep slope that comes down here, these step pool systems will begin to drain out. The water will drain out of the upper level, and if you have an enough extended period of time, the step pools will get lower and lower and lower, and they'll march on downstream, but we'll still have a perennial flow through it. But I wanted you to understand that this is how the thing's functioning after a fairly significant storm event. Another example of our eroding channel, this is a perennial stream. This is one that has enough, when it's not in this condition, has enough groundwater hydrology once we reconnect it here, where it has a very vibrant flow that extends over an extended period of time. Once again, disconnected from its floodplain, lost groundwater hydrology, sediment yield. This is an example of that same system after it has been refilled and reconstructed. Once again, a very good picture of the amount of floodplain area that otherwise has become resaturated and is working for us in terms of the reduction of nutrients, sediment and whatnot. This is another example of an area. This is one where there was a dam structure that created an impoundment for a private water system for a community. The dam structure catastrophically failed at a point in time. This is the sediment that accumulated within that system over time. The pilot channel that was flowing through here is meandering across that floodplain, continuously moving that sediment downstream. The next picture provides you a picture of our restoration of this. It's following very similar techniques that we're using on these other channels that I showed you, but we're in a wide floodplain area here, in a wetland area. The sand berms basically serve as a means for the water that seeps out of these steep slopes, flows through the sand berms. There's step pools as we march down through with riffles, so there's some grade control that's within this. If we go to the next slide, you'll see what the vegetation began to look like about a year after the project was constructed. And if we go to the next slide, you'll see what the system looked like after 5 years of its efforts of establishing itself. And you can imagine the ecosystem that we're evolving out of that. One more example here of an area. This was at one time was a natural bog system, and years ago, in infinite wisdom, the dredging occurred out in the waterway. They pumped all that dredge material up into that bog. It became a phragmites marsh. Using very similar techniques, this is the recreation of that system. In this particular case, we cut off the phragmites, we refilled the wetland area, capped off that material. And this is the ecosystem that has been created. Once again, it has incorporated within it very similar techniques as it relates to the rock weir structures. In closing, our goals and objectives and what we're trying to accomplish and achieve with the kind of work that we're doing in Arundel County is to stabilize these channels, to reduce the sediment yield, to reduce the phosphorus contributions that are coming out of that sediment as it flows downstream. Reconnecting these stream systems to the floodplain, restoring the groundwater hydrology, having a new ecosystem, aquatic ecosystem evolve over time within the system, and also to provide all of the resources for the fish passage, their habitat, the animal habitat, waterfowl, and ultimately our goal is to meet these designated uses within our waterways. Thank you.